Welcome back to Neural Intel. Today we're diving straight into a fascinating piece of AI research, AnimeGamer, infinite anime life simulation with next game state prediction. What grabbed me immediately about this paper is the ambition creating these endlessly evolving anime worlds where you can jump in with language and the AI keeps the whole thing consistent.
Absolutely. What's truly innovative here is the idea of infinite simulations with consistent characters and stories.
Hmm.
Existing AI can generate game elements or even, entire game scenes, but this aims for a persistent, evolving experience driven by your interaction.
Yeah.
Think of it less like playing a game with a fixed ending and more like guiding a character through an ongoing life story that unfolds, well, uniquely for you.
Exactly. So our mission today is to really unpack the technical wizardry that makes this possible. We're focusing on the AI models and how they're engineered to create this continuous coherent experience. Our main source, of course, is the research paper itself.
And to give you a mental picture, the paper showcases some really compelling examples. They demonstrate characters like Sosuke from Ponyo interacting in these AI-generated scenarios. What's interesting is that you don't just see the interaction, but also how the character's internal state, things like stamina, social connections, even how entertained they are changes in response, visualized through these dynamic bar graphs.
We also see examples with Kiki and Pazu from Kiki's delivery service playing out over multiple turns. You see them in different scenes, doing different things. And again, their character states are being continuously updated based on the ongoing interaction with the system.
Okay, let's jump into the core concepts. The paper starts by drawing a distinction between finite and infinite games. Now, this isn't your standard game theory. They're using these terms in a more philosophical sense, inspired by the work of James P. Carse.
Right. So a finite game is what we typically think of.
Hmm.
It's played to win, there are clear rules, and a definite endpoint, like a chess match or, a video game with a final boss. But what about these infinite games?
An infinite game, in this context, is played for the sake of continuing to play. There's no specific goal of winning or a defined end. The purpose is the ongoing interaction itself. Think of like improvisational theater. The scene continues as long as the participants keep it going.
Okay, see how that applies here. So where do current AI efforts in game generation typically fall? Are they mostly finite, or are they maybe inching towards this infinite idea?
Well, the paper categorizes them as either partly generated or fully generated. Partly generated approaches are more common. AI helps with specific aspects of game development within existing structured systems. Maybe AI designs a level or populates a world with NPCs, but the underlying game mechanics and overall structure are predefined.
So the AI is assisting, but not truly creating the whole unbounded experience.
Precisely. Then you have fully generated approaches where AI aims to create all aspects of a game. However, the paper points out that these often focus on replicating specific games or operating within very constrained environments. They might recreate a level from Minecraft or generate a simple platformer, perhaps, but they don't typically offer that open-ended, continuous experience that responds to natural language input.
And that's the key difference with AnimeGamer, right? They're shooting for this fully generative, infinite game. That sounds like a monumental challenge, especially when you're dealing with both text and evolving visuals.
It is a significant leap, moving from generating static scenes or assisting in finite games to creating a dynamic, persistent virtual world that you can influence with language requires overcoming some really fundamental hurdles.
One of the biggest, it seems, is maintaining coherence over these extended interactions. If you're having a multi-turn conversation and the AI is generating visuals, how do you stop the characters from suddenly looking different or the environment from changing arbitrarily? The paper mentions previous attempts with large language models, LLMs, and text-image T2I models struggling with this. Why is that such a tough nut to crack?
The core issue, well, it boils down to how these models traditionally process information. Standard LLMs are primarily focused on the text history of the conversation, the words you and the AI have exchanged. When you then try to use this text to guide a text-to-image model, the LLM's understanding of the visual world is somewhat limited. It doesn't have a strong memory of what the generated images looked like in previous turns, you see.
So the AI might generate a description that sounds consistent in text, but when the T2I model creates the visual, it might not match what came before, like Kiki's cat. Gigi might change color or suddenly grow wings.
Exactly. And this lack of visual grounding becomes even more problematic when you try to create coherent video sequences over multiple turns. Without a consistent visual reference point in the underlying AI, the generated animations can become jarring and, well, nonsensical.
Okay, so how does AnimeGamer address this core challenge of keeping things consistent across multiple interactions? What's the breakthrough here?
The central innovation lies in their use of a multimodal large language model, or MLLM. The key word here is multimodal. It means this language model isn't just processing text. It's designed to take in and understand historical multimodal context, meaning both the text of your interactions and the visual information that the actual generated animation shots from previous turns.
Ah, so it has a memory that includes both what was said and what was shown. That makes a huge difference.
Precisely. By having access to this richer history, the MLLM can make much more informed predictions about what the next game state should be, leading to better visual and contextual consistency over these extended interactions. It's moving beyond the short-term memory of text-based models to an AI that sees and remembers the visual world it's creating.
That sounds like a fundamental shift. Now let's get into the specifics of how AnimeGamer actually works. How does it take an animation shot and turn it into something the AI can understand and then regenerate?
The system uses something called an animation shot encoder, which they've named IA. Its job is to create what they call an action-aware multimodal representation, which they label as SA. Think of SA as a compressed digital fingerprint of the animation shot that captures both what it looks like and what's happening in it.
And how does it create this fingerprint? What information does it look at?
It takes two main inputs: visual features, which are extracted from the very first frame of the animation shot, and textual features, which come from the AI's understanding of the action that's being described.
Okay, so it analyzes the image and the text description simultaneously.
Mm.
How does it combine these two different types of information into that single representation, Sa?
According to the paper, the encoder IA first puts both the visual and textual features through some processing. They use multi-layer perceptrons, MLPs, think of them as translators maybe, to make sure the visual and text information can talk to each other effectively by aligning their dimensions. Then, they apply a normalization step to keep the scales consistent. Finally, they combine these processed visual and textual features together to create that action-aware multimodal representation, FES.
Got it. So SES is this combined understanding of the animation. What happens next? How does the system use SES to generate a new animation shot?
This representation, psi, then acts as a guide, a condition, for the animation shot decoder, which they call DAY. This decoder is built on top of a powerful existing video generation model called CogVideo-X. These types of models, known as diffusion models, learn to create realistic data by essentially reversing a process of adding noise. They learn what real images and videos look like by figuring out how to remove noise from random patterns.
Right. So the decoder takes this SA fingerprint as a starting point and then uses its knowledge of how to generate video to create a new animation shot that aligns with that representation.
Exactly. And there's another interesting element here. They also incorporate an additional piece of information called EMS, which represents the motion scope or the intensity of the action in the shot. This tells the decoder how much movement to include in the generated animation. This MS is also fed into the decoder using some mathematical techniques, sinusoidal embeddings, and fully connected layers to help control the animation.
So if the predicted game state involved a character running, the FMs would tell the decoder to generate an animation with a high degree of motion.
That's the idea. It adds another layer of control over the generated animation, making sure it matches the predicted action.
Building a system this sophisticated must require a massive amount of training data. How did they go about teaching AnimeGamer to understand and generate anime?
They used a two-phase training approach. The first phase was like a warm-up where they focused solely on optimizing the animation shot encoder EA. The goal here was to make sure that the SAW representation it created was in a format that the decoder, Dale, could readily understand. They wanted to align their languages, so to speak.
So they're essentially calibrating the encoder to speak the decoder's language.
Precisely. Then, in the second phase, they trained both the encoder and the decoder together. The training process involves showing the model real anime shots and their corresponding text descriptions, and then getting the model to reconstruct the original animation. They used a mathematical function, a loss function, to measure how wide the generated animation matched the real one, and they tweaked the model's internal parameters to minimize this difference, making it better at generating realistic anime.
The paper also mentioned something called decoder adaptation. What's the reasoning behind that?
Yes, because the MLLM, which is responsible for predicting the next game state, and the video diffusion model, which forms the basis of their decoder, were initially trained on different data sets, and for slightly different tasks, there's a potential mismatch in how they represent information internally. Their latent spaces might not perfectly align.
Okay.
To address this, they perform a decoder adaptation step where they fine-tune the decoder specifically based on the output of the MLLM. It's like fine-tuning a translator to better understand the specific accent of the speaker, in this case the MLLM, ensuring the generated anime shots are pixel-level accurate even when conditioned on the MLLM's predictions.
So it's a way to bridge the gap and ensure smoother communication between the different AI components.
Exactly. It helps the decoder better interpret and act upon the information coming from the MLLM.
Makes sense. Yeah, absolutely. Now, when you're proposing a new system like this, you need to show that it actually works and is better than existing approaches. How did they evaluate AnimeGamer and what did they compare it against?
Right. The researchers acknowledged that there weren't really any, off-the-shelf open source systems that do exactly what AnimeGamer aims to achieve, creating infinite interactive anime simulations. So they had to get creative and build their own baseline methods for comparison. They used Gemini 1.5, a powerful large language model, as a central hub in these baselines. This LLM was responsible for understanding the user's input and then generating instructions and character states for different image and video generation models.
And what were these different image and video generation models that they used in the comparison?
They combined Gemini 1.5 with 3 different generative models, which they referred to as GSC, GFC, and GC. Now, the paper doesn't explicitly detail what these acronyms stand for in the main text, but we can understand that they represent different approaches to generating the visual content based on the LLM's instructions. Perhaps one focuses on generating individual images, another on creating coherent video clips, and so on.
So these baselines represent alternative ways to try and achieve a similar interactive anime experience using more readily available AI tools.
Precisely. They act as a benchmark to see how AnimeGamer's more tightly integrated multimodal approach compares to systems that rely on a separate language model to guide more traditional generative models.
And how did they actually go about testing these different approaches? What kind of test scenarios did they create?
They developed a custom evaluation benchmark specifically designed for the task of infinite game generation. They used another powerful AI model, GPT-4o, to simulate these infinite games. In each simulated game, GPT-4o would randomly select characters from their training data and then generate a sequence of 10 rounds of interactions. For each round, it would create an instruction describing a movement or an environmental detail and also define the corresponding ground truth character states.
That sounds like a very comprehensive and challenging test.
Yeah.
How much data did the benchmark include?
It was quite extensive, comprising a total of 2,000 rounds of interactions. These interactions featured 20 different anime characters, 940 unique types of movements, and 133 distinct environments. This variety was crucial to really test the model's ability to generalize and maintain consistency across a wide range of scenarios.
And what specific metric did they use to objectively measure the performance of AnimeGamer and the baselines?
They used a range of both general and more specific quantitative metrics. To assess how consistent the characters looked across different turns, they used CLIPI, which measures the visual similarity between character depictions. For semantic consistency, how well the generated visuals and text align with the instructions and the overall context, they used DreamSim, CLAPT for text-image similarity, and CLIPTE for text-environment similarity. To evaluate the quality of the motion in the generated videos, they employed ACCF and MAEF. Finally, to measure how accurately the characters' internal states were updated based on the interactions, they used ACCS and MAES.
And how did AnimeGamer stack up against the baselines according to these objective measures?
The results, as shown in their Table 1, indicated that AnimeGamer generally outperformed the 3 baseline methods across most of these metrics. It demonstrated better consistency in how the characters looked, stronger alignment between the text and visuals, higher quality motion in the animations, and, comparable accuracy in updating the characters' internal states, all while maintaining a competitive processing speed.
Those automated metrics paint a positive picture for AnimeGamer. Did they also get any human feedback on the quality of the generated simulations?
Yes, they did. In addition to the automated evaluations, they also conducted evaluations involving both another powerful AI model, GPT-4v, as a judge, and human evaluators. The results of these subjective evaluations are summarized in their Table 2. Both GPT-4v and the human participants generally preferred AnimeGamer in terms of overall quality, how well it followed the instructions, its contextual consistency, the consistency of the characters, the visual style, and the accuracy of the state updates.
So it wasn't just the numbers, but also human perception that favored AnimeGamer. That's a strong indicator of its potential.
Exactly. It suggests that their integrated multimodal approach is indeed leading to more believable and engaging infinite game experiences, not just according to algorithms, but also to human eyes.
The paper also includes some interesting ablation studies. What are they trying to figure out with those experiments?
Ugh, the ablation studies. They were designed to dissect the AnimeGamer system and understand the contribution of its individual components. They focused on a specific anime film, Kiki's Delivery Service, and ran experiments where they selectively removed or modified certain parts of their architecture and training process to see how it affected the overall performance.
What specific parts did they tinker with?
One set of studies looked at the animation shot tokenization and detokenization process, how they convert the visual information into a digital representation and back again. They tested different ways of encoding the visual features, like using the first frame versus a random frame, different types of processing layers, and different methods for combining the visual and textual features.
And what did they learn from these experiments about their encoding and decoding methods?
The results, which you can see in their Table 3 in Figures 7 and 8, largely confirm the effectiveness of their chosen encoder architecture, particularly the use of the first frame to capture the visual essence of the shot and the concatenation of the processed visual and textual features. Interestingly, some alternative methods, like using cross-attention to combine the features, didn't perform quite as well in certain areas.
They also investigated the game state prediction and the decoder adaptation, right?
Yes. They examined how important that decoder adaptation step was, and also the impact of using a specific type of training loss called cosine loss, LCOS. What they found was that if they removed the decoder adaptation or didn't use the cosine loss during training, the performance of the system noticeably decreased. This highlights the crucial role these elements play in ensuring the quality and consistency of the generated videos.
And finally, they looked at the motion scope condition, FMS.
Exactly. They tested whether including that information about the intensity of the action in the decoder was actually beneficial. And indeed, when they removed F&Ms, they saw a drop in performance, confirming its importance in controlling the dynamism of the generated animation shots.
So these ablation studies provided valuable insights into why their specific architectural choices were effective.
Precisely. They helped to validate the individual contributions of the different components of the AnimeGamer system.
Lastly, let's talk about the data that fueled this research. Building a system like this requires a vast amount of relevant video data. How did they go about creating their anime video data set?
Creating this large-scale dataset was a multi-stage process. They started by collecting a large number of anime films. Then they pre-processed the videos by cropping any unnecessary borders and resizing them to a consistent resolution. To break the long videos down into manageable units, they used a scene detection model to segment the films into individual shots, and then further split these shots into shorter 2-second clips.
So they essentially chopped the anime films into a huge library of short video segments.
Yes, and to help the AI understand who the main characters were, they used reference images of the protagonists to locate them within each of these video segments. To get descriptions of what was happening in each shot, they used a powerful vision language AI model called Intern VL26B. They used specific prompts to get the AI to identify the characters present in each clip and describe the action taking place.
And how did they get the detailed information about things like the characters' movements, the environment, and even their internal states?
Again, they used carefully crafted prompts with Intern VL26B to extract the structured information. These prompts were designed to capture details about the subject of the shot, their motion, the surrounding environment, any adverbs describing the movement, whether there was any social interaction happening if the characters were engaged in any entertainment activities, and even an estimation of the character's stamina level for each short clip. This rich, structured data was essential for training their models to understand and predict the evolution of the game state.
Okay, let's bring this all together for our listeners. AnimeGamer represents a really exciting technical advancement in AI and interactive media. It's a significant leap towards creating these truly engaging and infinitely playable virtual worlds populated by characters we know and recognize.
What's fascinating here from a technical perspective is how they've tackled the long-standing challenge of maintaining coherence in generative AI. Their innovative use of a multimodal large language model that remembers both visual and textual information across extended interactions is really a key technical achievement. The sophisticated way they encode and decode animation shots to create dynamic visuals is also a crucial contribution.
And the rigorous evaluation framework they developed, including the creation of a specific benchmark for infinite anime games And the use of both automated metrics and human feedback provides a really solid way to assess progress in this complex and rapidly evolving field.
Definitely. If we consider the broader technical implications, the methods they've pioneered for maintaining multimodal coherence and generating dynamic content based on user input could have significant applications beyond just anime. Think about the potential for more immersive and responsive interactive storytelling, highly realistic virtual training environments, or even the development of truly personalized and context-aware digital companions.
Wow.
AnimeGamer's innovation in using multimodal memory offers a blueprint for persistent and coherent interactive AI experiences across diverse media.
So what does this all mean for the future? It really points towards a future where our interactions with AI-generated media become far more immersive, persistent, and truly interactive, blurring the lines between passively consuming content and actively shaping it through our language.
This raises an important question for you, the listener, to consider. What are the next big technical hurdles in creating truly believable and engaging infinite interactive experiences? How might the techniques explored in Anime Gamer be further refined and expanded upon to overcome these challenges and unlock even more immersive and dynamic virtual worlds? We encourage you to delve deeper into the research paper itself, which is linked in the show notes on our webpage, to explore these questions further.